Welcome to this pre-lab video for our next to last actual experiment in this course, which is the Electromotive Series. And in particular, we're looking at making an activity series based upon relative oxidizing and reducing strengths. So this video is going to kind of appear in two parts. The first part, I'm actually going to splice in an old lecture I did on how to balance chemical equations and how to balance redox reactions using what is called the half reaction method. And then after that, I'm going to jump in with a little bit about kind of how we can use the tables of standard reduction potentials to help with this activity idea, and how to use them to help make some balancing a little bit easier sometimes. And then we get into the pre-lab and the experiment itself. So if you're good with balancing reactions using the half reaction method, if you're good with balancing redox reactions in general, go ahead and feel free to skip ahead about 26 minutes or so to the end of that lecture video, and then kind of pick it up on the pre-lab side. Otherwise, we're going to go ahead and look at the actual pre-lab itself. So stay tuned after the jump.
Spend at least some of this time talking about the half reaction method. So this is the alternative method that can be used for balancing oxidation reactions. Now, like I said, this does have some utility in terms of electrochemistry. If you have to take Chem 2, you will see electrochem in that course. Redox reactions will be part of that because redox reactions run electrochemical reactions. And this is the way that they are presented in terms of these half reactions. But in terms of the balancing of equations using this method, what you'll find is that it is considerably a longer process. And so if you look at the process itself, there are 5 primary steps. Now, I say that a little bit tongue-in-cheek because step 3 here has many sub-steps within it to balance each half reaction in total and in turn. But it can be done. And so the process starts the same way. We start with oxidation numbers. We then use those oxidation number changes to split the reaction into half reactions, an oxidation half reaction and a reduction half reaction. And then our next step is to balance those half reactions, multiply the half reactions to make sure that the number of electrons coming in and the number of electrons going out are the same, and then do any kind of cancellation that is necessary. And so let's kind of get into the process a little bit here, and I'll kind of show it off. So for balancing, there are actually different procedures for balancing in acid versus balancing in base. So what I'll do is I'll show you the directions for how to balance it in acid, and then I'll show you how we tweak those directions just slightly to balance it in base. And so for balancing in acid, what we do is we first start by balancing everything that's not hydrogen or oxygen. Then we balance the oxygens using water. We balance the hydrogens using hydrogen ions, H+, and we balance the charge using electrons. And so we would do this for each of the half reactions. And then we'd go back here, and once we had our half reactions, we would multiply them to make sure that the electrons that are being left out by the oxidation are being taken in by the reduction. And then we add them together and cancel anything that's common on both sides. Now, if we are in base, it's very, very similar. The only difference is that at the very end, and I'm talking the very end, this step 5 end, at the very end, we simply convert the hydrogen ions and hydroxide ions and interchange them with each other. And how we do that is we add equivalent amounts of hydroxide to each side. And so that's how we get it to remain balanced. The hydrogen ion combines with the hydroxide ion to make water. The hydroxide ion on the opposite side stays hydroxide ion, and we'll have extra water molecules left over, and we'll just end up canceling them out. So this says that we're going to balance it in acid only. We're going to balance it in both using the half reaction method just to show it off. So our first step in this method is the same as the first step it was in the previous method as well, assigning oxidation numbers. So oxidation number for manganese here is +2. The oxidation number for the bismuth here is +5. And for the oxygen, it's -2. For the manganese is 7. And oxygen is -2. And in the bismuth, it's a +3. So this is our process. We've got everything set up. Now we just need to break it up into half reactions. So for our oxidation half reaction, we can see that the manganese is going from +2 to +7. So that's going to be the reaction that we are starting with. Manganese +2 turns into permanganate MnO4 -1. And our reduction half reaction, leave a little space, our reduction half reaction is going to involve the bismuthate ion, BiO3-, turning into bismuth 3+. So this is the reaction that's going on in both circumstances. Now our first step would be to balance everything that is not hydrogen or oxygen. And in this case, it's pretty easy. I have 1 manganese on this side, I have 1 manganese on that side, so that one's balanced. I've got 1 bismuth on this side, I've got 1 bismuth on that side, it's balanced as well. So that part's taken care of. Second step, I need to balance oxygen by adding water to the opposite sides. So I have 4 oxygens here. That would require 4 water molecules on this side. I have 3 oxygens here. That would require 3 water molecules on this side. The next step would be to balance hydrogens using hydrogen ion, H+. So I have added 8 hydrogens in total to the reactant side in the oxidation reaction. I'm going to need to add 8 hydrogen ions on the product side to counterbalance it. I've added 6 hydrogens in the form of water here. I'm going to need to add 6 hydrogen ions to the reactant side to balance it out. And then my last step is to balance electrons, or excuse me, to balance charge using electrons. So very similar to the process that we did before. I need to draw a line down the middle.
Mr. Burke.
Yes, Chastity.
Okay, it's a quick question. If it was hydrogen, if it was an equation with hydrogen, you would just need to add the oxygens. If it wanted it acid only.
So if it wants it in acid only, your first step is still to balance the oxygens. And if there were hydrogens on this side already, I would just take that off. So let's say that there was already, there's already 2 hydrogens over here on the reactor, right, or on the product side. I would only add 6 hydrogens instead of 8.
Okay. Go ahead. Okay, I'll process it.
Okay, so we're to the part where we're evaluating charge. Excuse me. On the reactant side, I've got a +2 charge from the manganese, and I've got 0 charge from the waters. So total charge on the reactant side is +2. On the product side, I've got a -1 from the permanganate and 8 positive ones from the hydrogen ions. Total charge over here is +7. And so I would need to add 5 electrons to this side to get rid of that extra positive charge. And so the electrons always go on the side that is too positive, that has extra positive charge. And so now I've got those charges to even out. I can rewrite my half reaction. My half reaction is going to be manganese 2 positive plus 4 waters makes permanganate ion plus 8 hydrogen ions plus 5 electrons. And so this is my oxidation half reaction. For the reduction half reaction, we've handled everything so far other than the charge. Total charge, I have a -1 from the bismuthate ion and 6 positive ones from the hydrogen ions. Total charge over here is +5. And on the other side here, I have a +3 for the bismuth and 3 uncharged water molecules for a +3 over here. To balance the charge, I need electrons. So I'm going to have to add 2 electrons to this side. And the 2 electrons are going to take that +5 to a +3 so that the +3s now match up. In a similar fashion, I've got everything balanced up. Let's go ahead and write the half reaction. It's BiO3 -1 plus 6 hydrogen positive ions and 2 electrons, making Bi +3, bismuth 3 ion, and 3 waters. Okay, and so with these two half reactions, this is, we've only gone part of the way. We are now through step 3 of our 5-point procedure that we talked about. The next step is we have to evaluate the number of electrons that are leaving the manganese versus the number of electrons that are coming into the bismuth. And we can see that the two are not equal. 5 are being deposited by the manganese, 2 are being turned into the bismuth. And so we need to equal it out so that just as many are leaving as are coming in. And just like we did in the previous method, the way to do that is through a lowest common multiple. The lowest common multiple between 5 and 2 is 10. So I'm going to multiply both equations by a number to get them to 10 electrons either gained or lost. And that means that I'm going to have to take the manganese half reaction, multiply it by 2, and the bismuth half reaction and multiply it by 5. And so what this will look like afterward, 2 manganese positive 2 plus 8 water makes 2 permanganate ions, 16 hydrogen ions, and 10 electrons. And if we add that to our other half reaction, 5 bismuthate ions and 30 hydrogen ions and 10 electrons make 5 bismuth 3+ ions and 15 waters. Those are our two half reactions. Now we can see that I have equal amounts of electrons on each side. Since I have that, I can now combine them together, and I'm actually going to have to put the result down a little bit lower here because it's going to take up a lot of space. So the net result, which we'll put here in black, is 2 manganese positive 2s, 8 waters, 5 bismuth 8 ions, 30 hydrogen ions, 10 electrons, 2 permanganate ions, 16 hydrogen ions, 10 electrons, 5 bismuth 3+ ions, and 15 waters. This is the balanced equation that we would run into. Now, there is some extraneous, there's some fluff here. There are things that are common on both sides that would be in our best interest to get rid of. In particular, we can look and see that I have water common on both sides, I have hydrogen ion common on both sides, and I have electrons common on both sides. So similar to what we saw in net ionic equations yesterday, we are going to want to cut some of the things that are common because they cancel out. So the 10 electrons can cancel out. Let's see, I have 8 waters on the reactant side that can negate 8 of those 15 waters on the product side. So that 8 becomes a 7. And I've got 16 hydrogen ions on the product side that can negate 16 of those hydrogen ions on the reactant side. And so if I do one more rewrite here, the final equation in acid is 2 manganese ions, 2 manganese 2 plus 5 bismuthate ions, plus 14 hydrogen ions make 2 permanganate ions, 5 bismuth 3 plus ions, and 7 waters. That is the final, at last, equation for this reaction in acid. So, like I said, individually, oxidation half reactions, reduction half reactions aren't too terribly difficult to do. And even in the combining out process, this isn't terribly difficult. There is a reason why this method is preferred by some students and by some faculty members for that matter. The bottom line is the hard part is really there's a lot of process. There's a lot of steps in here. It took us 20 minutes to do this problem. Whereas in the same light, we did in 20 minutes acid, base, and part of a third reaction using the other method. So there is some utility to this. Don't get me wrong. I'm not going to completely bash this technique, but it is a good bit deal longer. And there are lots more steps to do, lots more mistakes that can be made along the way. And we haven't even done the base part. For the base part, if we take this equation up here, to convert it into base, what I need to do is there is no H plus, or at least very little H plus, available in base. So what we do to more or less combat that is we're going to add equal amounts of hydroxide to each side of the equation. When we do that, it's going to turn the hydrogen ions into waters. And the second thing it's going to do is it's going to create another situation where we have to cancel, because I'm going to have waters on each side. So these 7 waters negate 7 of those waters. And so the net result for base would be 2 manganese, 2 pluses, 5 BiO3 minus bismuthate ions, 7 waters, making 2 permanganate ions, 5 bismuth, 3 ions, and 14 hydroxide ions. And so once you get it in acid, turning it into base isn't usually that difficult. Sometimes, if we find that our hydrogen and our water are on opposite ends, literally all that happens is that it flips around. The waters move over to the reactant side, the hydroxides move an equal and opposite number to the product side, or vice versa. Where it gets a little bit complicated and tricky, there are some occasions because of hydrogen content in some of the reacting species where water and acid end up on the same side of the equation. And then that's the case where you can't do that. And you have to actually go through and do the math. But if hydrogen and water are on opposite sides of the reaction, then literally all they do is switch places, and the H plus becomes OH minus. And that's how you fix it for a base as opposed to an acid.
So now let's get into the actual material for this particular lab and pre-lab activity. So what's really going on and what we need to focus on is we're looking at redox reactions. In particular, we are looking at reactions involving the substances acting as oxidizing agents or producing agents. So as the clip that I showed you before kind of indicated, there is a way of going through this very systematically to determine whether or to determine what the balanced chemical equation would look like. However, what that doesn't really cover is the idea of whether or not a reaction would even occur in the first place. Plus, that process can be a little bit cumbersome to deal with. So we have to have some other things involved along the line here. So I'm going to show you some things that can actually help us in terms of framing that conversation and looking at things from a perspective of whether or not a reaction would occur. So this is out of your appendix tables. These are called standard electrode potentials. These are all reduction reactions. So what we are looking at in these reduction reactions are the ability of a substance to add electrons, to become reduced. And so in a way, we're looking at how well these substances are going to be reduced, how good of an oxidizing agent they ultimately are. And so what we can look for in this is we're going to see two things. We're going to see the full half reaction. So imagine that you went through that whole process of balancing the half reaction, and depending upon whether you were in base and therefore you had hydroxides, or acid and therefore had hydrogens, you could evaluate each of those kind of accordingly. Now, for the ones here that don't have hydrogen or hydroxide in them, those particular reactions are amphiprotic in a way, in the sense that they are going to be the same in acid or base regardless. So what does this ultimately tell us? Well, it tells us, for example, that aluminum in the ionic form, aluminum ion is a terrible oxidizing agent. These values, which can be negative or positive, the more positive they are, the more likely that substance is to being reduced. So aluminum on its own, terrible oxidizing agent. But the thing is that's funny is if we reverse the reaction, the sign of the potential reverses as well. So if I have aluminum turning into aluminum ion and its electrons, well, the standard reduction potential for that, or excuse me, the standard potential for that would be positive 1.682 volts. So what that tells us is even though aluminum ion here is a terrible oxidizing agent, aluminum metal is actually a pretty good reducing agent. So one of the things that I can do with this information is I can look at one of the reactions, like say what's in your experiment, where, okay, we've got copper 2 ion reacting with zinc. And I can look at it and determine, okay, is that reaction actually worth anything? Is that going to happen? Well, I can look at copper 2. So we get down here to where copper is. And we see that the reaction between copper 2 and copper actually is a net positive. This is a reaction that is favorable. So copper 2 and turning into copper is 0.344 volts. And if I compare that to zinc, zinc being way down here at the bottom, I can see that the reaction involving zinc is not very favorable at all. Zinc doesn't want to add electrons. In fact, zinc would much prefer to lose electrons. Zinc turning into zinc 2 plus and 2 electrons. That process is favored, 0.761 volts. So what we have is we have a reaction where the thing that wants to add electrons is more likely to add electrons than the thing that doesn't want to add electrons. So I can compare their values to each other and say, yeah, copper 2 plus is a much better oxidizing agent than zinc 2 plus. And because of that, and because that's what we have, the copper 2 plus and not the zinc 2 plus, that reaction is going to occur. And all I have to do to write out the balanced chemical equation is just combine these two equations together. Copper 2 plus and 2 electrons and zinc turning into zinc 2 plus, 2 electrons, and copper. And notice that I have 2 electrons on both sides, so those cancel out. My balanced chemical equation is just the copper 2 plus reacting with the zinc to make zinc 2 plus and copper. The copper is getting reduced, the zinc is getting oxidized. The copper 2 plus is our oxidizing agent, the zinc is our reducing agent. So this is a way that we can use these standard reduction potentials to kind of help us figure out what's supposed to happen, what's not supposed to happen. Now, another thing that they can do for us, again, since they're already balanced half reactions, We just need to manipulate them to the proper equation. And if we do that, all we need to do is make sure that the electrons cancel out. So we multiply the equations accordingly to get that to happen. And then we just add what's left, cross out what's common, and rewrite what didn't get canceled out. So that's kind of a way around the half reaction method if we have reduction potentials available to us. Now, if we don't, we're going to have to go through that process that was described in the material before this part of the video. So let's turn our sights to the actual experiment itself. So in this experiment, you're going to do a series of reactions. The series of reactions you're going to see in part 1, you're going to do 6 chemical reactions, looking at different combinations of substances with each other. And notice, reaction number 1, we're doing copper 2+ and zinc. Reaction number 4, we're actually doing the opposite of that. We're doing the zinc 2+ and copper. Now, with that understanding of reduction potentials in mind, we know that one of these is going to work and the other one will not. And we've already kind of proven that this one is going to take place because the reduction potentials tell us that the copper 2+ is a much better oxidizer than the zinc is. And so for that reason also, we're not going to see anything down here. So with the reduction potentials, we can actually predict how all 6 of these reactions are going to go. We don't have to. We're certainly not going to force it, but we could if we wanted to. So that's one thing that's going to happen. So you've got 6 observations, 6 reactions to run in part 1. And from those reactions, you are going to rank the copper 2, the silver, the zinc, and the hydrogen ion from weakest to strongest. In part 2, you're going to look at the 3 halogens, chlorine, bromine, and iodine. 6 reactions there as well. And again, with our table of values here, we'll be able to compare the oxidizing potential of chlorine, which is actually pretty good, compared to that of bromine, which is good, but not as good, which will lead us to believe that the bromine actually is going to be a weaker oxidizer than the chlorine. The chlorine is going to be more reactive and dominate the bromine anytime that they come into contact with each other. And then finally, part 3, we're going to kind of look at how those 2 tables that were separate, so how the 4 substances in part 1 mesh with the 3 substances in part 2, to put it all together in one final table. Now, looking at the pre-lab here, a couple of questions that are going to come up. So first of all, number 1, in order to identify strength, we have to observe reactions occurring. What are some observations that lead someone to the conclusion that a reaction had occurred? This is very general chemistry 1 kinds of stuff. These are things like forms of solid, gas forms, heat, all of those things that we talked about when we were trying to figure out what is a chemical reaction way back at the beginning of Chem 105. That's the kind of stuff that's going to show up here. So for number 2 here, you see that you're going to have 2 reactions that you're going to have to balance. You will have to balance this using the half reaction method because the reactions that you're being asked to do are not going to appear in these tables. So while you might be able to find some of the values, you're not going to be able to find all of them. You'll have to still do the full process anyway. So don't even bother with the appendix tables. Just go straight into the process like it was described in the previous question. And then number 3 here, number 3 is asking us to more or less evaluate experimental results. So we're told that we have a piece of calcium here and it reacts with HCl. So what that is saying is I had calcium metal and hydrogen ion, and we see evidence of the reaction. It gets warm, there are bubbles. So we know that the calcium, well, has no real choice. It's going to oxidize, and the hydrogen is going to reduce. So what does that tell us about the relative positions of those two to each other? Since this reaction occurred, that means that hydrogen ion is going to be a better oxidizing agent than calcium ion is. Now, on the flip side, calcium metal is going to be a much better reducing agent than hydrogen gas is, but that's not what's going on here at all. So comparing those two to each other, we're going to be able to make that kind of observation. We can also look at the idea of we've got calcium metal reacting with lead 2 nitrate. And we see that we've got a black solid that wasn't there before. So we know that the calcium ion and the lead metal is what is causing that black solid. So from that position, we know that the lead ion is better than the calcium. So our weakest oxidizing agent of these three is the calcium ion. And so I can put that oxidizing, that reduction reaction here in that weakest column, because we know that the calcium ion is not a very good oxidizing agent because the calcium metal is so darn reactive. Now, I'll leave you to interpret that third one on your own so that you can arrange those two accordingly. But that is what you have to do for this last part. Look at the reactions, note the changes, and evaluate. Okay, this reacted, so that means that this is a decent oxidizing agent. This reacted, that means that it's a better oxidizing agent than calcium. So I can start to kind of rank them accordingly. So that's it for this particular lab. There's going to be a lot to unpack as you go through this experiment. So as we're kind of going through this, as we're making our observations, we're probably going to be stopping periodically just to kind of make sure we understand what it is we are seeing and what it means ultimately. So that's all for this video. Please let me know if you have any questions along the way. I'll be glad to help you out as we get ready for that lab itself. But until next time, I'll see you in lab.